So, hi everyone. Am I audible? Hello. Charan,
Yes,
am
sir.
I audible?
Yes, sir.
Hi, my name is Ravi. So, I have 4 years of experience in this VLSI industry. So, I'm here to discuss about how the VLSI industry. So, what are the things we have in VLSI industry? So, what will be the semiconductor industry after 3 years? So, we'll discuss about these topics by the end of this section. So by end of this section, we are going to discuss about what is VLSI. So we will know a brief introduction. We know what is VLSI. So what are the things we need? What are the things we have in VLSI? So why we need to learn VLSI? So what are the different types of domains we have in VLSI? And why VLSI companies are paying a lot of salaries, a huge amount of salaries to their VLSI employees? And how will be the VLSI market or how will be the VLSI industry in past 3 years, in next 3 years? So we're going to discuss about these topics by end of this section. So by end of this section, we are going to learn about these things. So we'll start with introduction to VLSI first. So what is mean by VLSI? So the abbreviation of VLSI is very large scale integration. So what is mean by very large scale integration? Is nothing but integration of billions of trillions of transistors inside a chip we are calling as a VLSI. So why we need to integrate billions or trillions of transistors inside a VLSI? So why we need to do that? Since because so we need to design a chip, we need to design a chip with less cost, and we're going to decrease the size of the chip, and we're going to increase the performance of the chip. We need to integrate the transistors inside a chip. So what is mean by transistors, sir? From the starting onwards, I'm saying transistors. So what is this? What is mean by this transistor? So transistors are nothing but a switch where it is allows to pass the current through it. So when it meets the threshold voltage, so threshold voltage is nothing but a control point. So it have a specialized voltage. So when it meets that voltage, when the current meets that voltage, so what will happen? So electrons will flow through the transistor. So that is the meaning of transistors. So transistors are nothing but a switch where it allows you to pass the current through it when it meets a threshold voltage. Okay, so this is what transistor means. So this VLSI technology was introduced in 1970s. So why they came with VLSI technology? Because they came up with an idea to integrate multiple circuits. Like we have different kinds of circuits, right? Adders, full adders. So to make the circuits or integrate the circuits inside a single chip, so they came up with this idea, and they're going to integrate that circuits inside a single chip, and they came with this idea. They came into this industry, and they had did it, and they made a foundation step to design a VLSI chip. So the VLSI foundation step was, or foundation stone was done in 1970s. So why they need to do that? So why they need to integrate multiple circuits inside a single chip? So to reduce the size or to reduce the cost or to increase the performance of the circuit, so what they had did is they are going to integrate multiple circuits inside a single chip. So they came up with this idea, and they had did it, and it has been success in 1970s. And that was the stone they had done. That was the foundation stone they had built to design these chips. So the first chip was introduced in 1970. So they had done with 10 to 20, 120 transistors. So they had designed a circuit, or they had designed a chip with 120 transistors. So the size of the transistor and the technology, what they had used is 10 to 20 micrometers. Okay, that means 10 power minus 6. So the size of the transistor is 10 power minus 6. So when in 1970s, so the size of the number of transistors they had used to develop the circuit is 120. So with 120 transistors, they had designed the chip. So while coming to now, they are inserting in the same chip, we are inserting billions or that means more than 10,000 transistors are integrating inside that. Just wait a minute, guys.
configure port.
So sorry for the disturbance. Okay. So in 1970s, what they had did is, so they had tried to integrate multiple circuits. That means multiple adders or full adders or half adders or whatever the circuits may be. So they're trying to inbuild inside a single chip. So they done it 1970. So that made a foundation step to design any chip. So after that, what they had did, so they had tried to design a chip. So they had the Intel company has tried to develop a chip which we call as 8086 microprocessor. So they had done it with 120 transistors. So that microprocessor is used in your calculators. Currently, we are using that microprocessor in calculators. So what they had did is, so they had designed the chip at 1970s with 120 transistors with 10 to 29 micrometers of technology, with 10 to 20 micrometers of technology. By using the technology, so they had developed a chip. And currently what we are doing is, within a same space or within a same chip, we are integrating billions and trillions of transistors. And the technology currently what we are using is 2 nanometer technology. So see, from past 1990s, 1970s to from 2025. So currently we are using 2 nanometer technology, that is 10 power minus 9. That means to see how the size of the chip, so that we can't able to see that much of size of transistors we are developing, and we are integrating a chip. Okay, so where we are going to use these chips, so what was the real-time applications of this? So mostly we are going to use these chips in our mobiles, laptops, are going to use inside our TV remotes. So mostly, or yeah, we have Tesla car. So the Tesla car is fully developed with chips only. So mostly we are going to use these chips in those kinds of real-time examples. So usually if you see the chip, what are the things there inside a chip? So if you think it's chip is like a, so I'm going to take a laptop as an example. So inside a laptop I have a chip, right? So I have a chip inside a laptop. Let's say this is my chip. So inside a chip, so we are going to develop a chip with multiple IPs. So that means we'll have a several blocks inside a chip. So let's suppose we'll take a this laptop. So inside this laptop we have multiple blocks. So we have a memory. So we have a HDMI cable, and we have a USB ports, and we have a processor, and also we have some ports, other ports. So what are the ports we have? So we have several ports inside my chip. So how these blocks are going to be connected? So these blocks are going to be connected with buses. So we have a bus concept, we have an ARM concept. So by using those ARM, so it is fully made up of buses. So this concept it is going to be tell how the data will be flow in between one block to one block. So these connections are made up with blocks. That means I'm going to transfer the data from one block to another block. So it is done through only buses. And we have an other blocks. So these are the blocks, right? So each and every company will make these IPs. So these blocks we are calling as an IPs, intellectual property. So each and every company will make their own IPs. And so when we are designing a chip, so no all blocks won't be designed by one company. So if you see for Macron company, so Macron is fully developed with memories. So that they are specialized in designing memories. We are coming to Intel. So what Intel will do, they are going to develop with processors. They are good in processors. They are going to designing the processors. So once some other company want to come and they want to design a chip. So how they will design the chip. So that company won't have all these blocks, right? So all these blocks won't be there for all the blocks won't be there for each and every company. So each and every company are specialized in one block. So what they will do is they are going to buy these IPs from that company. So that we are calling as a vendors. So we are going to buy that IP from that block from that company, and we are going to integrate in a our on USB port or use PCB design or whatever the thing. So we are going to integrate it in our chip, and we are going to make the design, and we are going to design a chip. So this is how it normally chip is getting made. Okay. So the next one is, so what is VLSI design block? So in this, so we are going to discuss about, so VLSI basics. When we want to learn VLSI, what are the currently things, what are the basic things we need to learn? So how will be the VLSI design flow? So what is front end and what is back end in VLSI, and how will be the chip is manufactured, or how will be the fabrication centers, and how will be the careers in VLSI after 3 years? We are going to discuss this now. So the first one is basics. So what are the basics that we need to learn VLSI? So what are the basic? The basic building block to design any digital circuits is transistors. So transistors is the basic building block, right? So transistors, by using transistors, we are going to design our gates. So transistors are made up of CMOS. So CMOS means complementary metal oxide semiconductor. So by using these transistors, what we are going to do is, if so, these CMOS is developed with one PMOS and one NMOS. So by combining of one NMOS and one PMOS, we'll get one CMOS. So this is nothing but a inverter gate. So by using inverters, we are going to design gates, AND gate, OR gate. So by using gates, we are going to design our logics. By inserting some logics inside that gates, what we'll do, we'll design one combinational circuit. So for the combination circuits, if you insert in one memory, what it will happen? So it will become sequential circuits. So by using sequential circuits, we are by combining all these circuits and making some logical in between them, we can design a chip. So how it will be, we'll discuss now. So basically the chips are of two types. So one is ASIC and one more is FPGA. So these are the two types of chips what we have. So or we can ASIC, or we can also say it as SoC, system on chip. So ASIC means application specific integrated circuit. That means we are going to design a chip only for the specified applications. So that we are calling as a ASIC. So if you, the real time examples what I can say for is mobiles. So we have, if we design a mobile, so if we design a chip for a mobile, so we can use for only for the communication or for the watching videos, only for the certain things we can do. So can we insert the chip for these laptops? To design laptops, can we insert that? So it is not possible, right? So if you want to design a chip for the specific applications, we are going to use this ASIC chips. We're going to use this ASIC chips. And the next one is FPGA. So field programmable gate array. So this is reusable one. That means once if you made this chip, so we can reuse. So that means suppose if I use this chip for mobiles, and after that I can erase the data what we have inside that, and I can use it for another purpose. So that we call as an FPGA. So that is multiple purpose. These FPGA chips are used for multiple purpose. So but ASIC is not like that. So these are the two types of chips what we have. So how we are going to do that is, we are going to take the IPs from the companies, whatever the based on the specifications what we have. So we are going to take that and we are going to integrate that in a PCB board, and we are going to design that circuit. So this is how a chip is getting made. So we'll see how this okay, the next one is about CMOS to full processor. So how the things what we are learning basics. So how the basics are helpful to design a chip. So how we are going, how it is getting help is, so the first stage of basic things what we need to learn is about CMOS, right? So by using CMOS, we are going to learn about why we are going to design the gates. By using transistors, we are going to design the gates. So by using gates, so by applying some logical operation inside the gates, what we can do? So we can design the combination circuits. We can design the combination circuits. So how a combination circuit is going to work? So if you see a combination circuit, so combination circuit consists of several inputs and few outputs, and some logic gates will be there inside that block. So that logic gates will be arranged in a specified manner. So if you want for full adder, it will be there in one mode, and if you want to see for mux, it will be there in another mode. If you want for another circuit, it will be there in another mode. So for the combination circuits, the output will be depends upon whatever the input we are passing. So whenever the data we are passing, and whatever the input we are passing, at the same amount of time, we will get the output. So this is what combination circuit will do. So if we, but while coming to sequential circuits, so the output will be the output. If you want to find the output of sequential circuits, so it won't be, it not only depends upon the input, so it will be depends upon the previous output also for the sequential circuits. So for that, what we need here, so we need to store the previous output. But what for that, what we are going to do is we are going to add one memory. We are going to add one memory to our combinational circuits. So then what will happen? The memory will store the previous output, and we are going to apply the present inputs. So I change my input, so the output of my sequential circuits will be seen from the memory and as well as inputs. So this is how a sequential circuits is going to work. So while coming to combination circuits won't store any data. So it won't store any data. While coming to sequential circuits only, it is going to be store the data. So since because it having a memory to store the previous value, right? So that's why only the sequential circuits can store the data, and as well as combination circuits won't store any data. So this is what. And the next stage what we have is we are going to develop the core processors, the core things of a core blocks of a processor. So what was the core processors? ALU, control unit, and program unit are the core blocks of my circuit. So what ALU going to do? So ALU is going to do some logical operations, and after that it is going to execute that operations and will give the respective output. And what this control unit is going to do? So control is going to, it is going to do or execute some instructions. So for if your process is need to work, so we need to give some instructions, right? So we are going to give the instructions in form of high level language, and that high level language need to be converted into low level language, that means binary code. So that things will be done in this control unit, and it is going to be converted your high level language into low level language. And what it will do, and it will execute the instructions what we have in it. And what we at a time we are going to give multiple instructions. There is a chance of giving multiple instructions at a time. So what it will do, so who will control that? So if it only a single instruction can do at a time. So if I give multiple instructions, what I need to do? So it need to be there in a sequential, right? It should be executed in a sequential order. So that instructions will be set or carried out by this programming counter. So it is going to be specify the next instruction. So what was the next instruction that need to be execute? So that will be sent by this programming counter. So this was the things there in stage 5. And after that we have a memories. So and after that we are going to have a memory interfaces, and also we have buses, and also we have input output interfaces. So what memory interface is going to do? So it is going to write the data inside a memory, or it going to read the data inside a memory. So that is the purpose of memory interface. The next one is buses. So what buses will do? So it's going to carry the information from one block to another block. So this was the purpose of buses. And next one is input output interfaces. So these input output interfaces is used to connect your device to an external device. So suppose we have what I can say for it is, so I have an USB port. So I want to connect that USB port to my memory. So how I'm going to do? So I have that USB port to my receiver, and I have to it to my input, right? I'm going to connect that, and what will happen? So the external part. So mouse is my external part. So external part is connected to my board. So this is how, right? So these connections is done through input output interfaces. So that is what input, that is the purpose of input output interfaces inside your chip. And next one is by combining of all these, by combining of logical gates or combination circuits or sequential circuits or ALU or memory. So we are going to design our chip. So this is the how. So I'm here to teach you why we need to learn basics, why we need to learn basics to design a chip. So if you want to design a chip, you need to know about all these things. When you know about all these things, then only you can design a chip. Okay. So this was the thing. So this is how CMOS is getting helpful for starting to until the chip is getting made. So the next one is how the transistors are getting evolved. So how the transistors are getting evolved from small scale integration to large scale integration. Small scale integration is nothing but, so when we are usually developing a chip, so usually what was the transistors count inside a chip? So when coming to 1970s, so the transistors count is in between 0 to 120. So it is in between 0 to 120, right? So but later on, when we are days are going on, so how the transistors count is getting increased day by day. So the transistors counting is currently, now it is in trillions or billions of transistors we are integrating in a single chip. So based on the number of transistors inside a chip, so they are categorized into different ways. So they are categorized your circuits into different types. So one is small scale integration. So another one is medium scale integration, large scale integration, and very large scale integration. So these are the four different types what we have. So small scale integration is nothing but when the chip contains 0 to 100 number of transistors, then we are calling as a small scale integration. So if you have a transistors count in between 0 to 100, then we are calling as a small scale integration. So while coming to large scale, medium scale integration, so the transistors count is there in between 100 to 1000. So the count of transistors what we have in a chip should be there in between 100 to 1000. So if it is in between 1000 to 10,000 or 10,000 to 1 lakh. So if it is there in between 1000 to 1 lakh, then we are calling as a large scale integration. And we're coming to large scale integration, it is from 1 lakh to billions or trillions of transistors. More than 1 lakh number of transistors if we have inside a chip, then we are calling as a very large scale integration. So currently we are doing with very large scale integration. Okay. So where we use the small scale integration? So gates. So gates contains less than 10 number of transistors. So this is also a chip, right? So we can see for so what was ICs or what are the chips we have seen in our BTech. So we have seen gates, so which is having two inputs. So we have done a lot of projects in our BTech level, right? So that is that we can consider as a small scale integration. So we have seen mux, right? Mux 82 to 1 mux or 16 to 1 mux. We have seen on auto mux. That mux we can say as an example for medium scale integration. So while coming to adders or full adders or sorry, not full adders, shift registers, which is having more than that, right? So that we can say as an example for large scale integration. And next one is very large scale integration is nothing but our mobiles, which is having billions of trillions of transistors. That we can say as an example for very large scale integration. So next one, what I want to discuss is about transistor timeline. So from transistor is developing to the till end. So what they had did. So that first transistors was developed in 1947 and 1948. So they had developed um, junction transistor. So they had developed junction transistor in 1948, and with the transistor they had developed radios and computers. So they had developed with radios and computers. Currently we are using silicon transistors. So they had developed junction transistors in 1948, and they had developed few radios and few computers. They had developed with few computers. And coming to 1954 to 1958, from coming to 1954 to 1958, so they had developed silicon transistors. They had developed silicon transistors. So with that silicon transistors, what they had did is, so they developed cars. So they developed satellites. So those, with the transistors they had developed this. And after that, what they have happening in 1959, they had developed transistors. So they had developed MOSFET transistors. So they had developed MOSFET transistors in 1959. And after that, what they had did is, with that MOSFET transistors, they had developed your mobiles, computers, or telephones, or else everything has developed. And after that, from 1959 to till end, so what they had worked on, so they worked on to decrease the size of the transistor. So they have when they are developing the transistor, the size of the transistor is 10 to 20 microns, right? So after that, they are tried, so they won't develop any other transistor. So what they had worked on is, they are worked on just decrease the size of the transistor. So when they are designing a transistor, let's say the size of the chip is 10 power minus 3 micrometers. Now it is 10 power minus 9 nanometers. That means, see how the transistor size has been decreased. So they worked on it. So they with the transistor, with that technology, they had developed the current chips what we have. And in 1965, what they had did is, so they introduced a Moore's law. So what Moore's law is going to say is, so for each and every 2 to 3 years, the transistors count is getting doubled inside a chip. So that is what they had found in 1965. So and they had named it as a Moore's law. So what is Moore's law? For every 2 to 3 years, the transistors count inside a chip is getting doubled. So that is what they had observed by seeing the chips, by seeing the chips. Okay. So this is all about timeline of transistors. So the next one is transistor evaluation. So while coming to 1971, so in 1970s where they had developed. So see the transistors count 2300. So it is almost of 2000. It is started with 120. So but while coming to 120 in 1970. In 1971, they had some more, they were some more increased, and it is with 2300. And currently, what was the transistors count in 2011? In 2011, it is almost of 26 billions or trillions. It is there. So see, so this is this by seeing this graph, we can say like it is obeying the Moore's law. It is obeying the Moore's law. So that is right. So while coming for comparison with 1970s and 2011, so they increased a lot of transistors inside the chip, and it is obeying the Moore's law also. Okay. And the next one here, what we are going to discuss about VLSI design flow. So what are the things when you want to design a chip, when you want to fabricate a chip? So what are the things we need? So what are the things? What are the different kinds of stages we have? So we are going to see now. So when you want to design a chip, what was the first thing we need to know? So we need to know the functionalities of it, right? So we need the functionalities of it. We are going to know, or we need to know. So we'll discuss that. So first stage is about design specifications. So we need to know the specifications of that circuit. Next one is RTL design, RTL verification. Next one is RTL verification or functional verification. And after that, logical synthesis, physical design, fabrication and packing, and testing and production. These are the different stages what we have. So along with that, we have different other stages also. So we'll see that. So specification of a application, specifications of application. So when you want to design a chip, the first step is to know the specifications. So how we are going to provide, how we are going to say the specifications. So if you want to say the specifications, we need to say what was the functionality of the chip, so how it should be worked, and what was the size of the chip, so what was the technology we are going to use, and what was the things we need to do. So everything we need to say, so that things will be specified inside a specifications. But those are the specifications we need to specify in the design specifications block. That is the first stage. And while coming to the next stage, we are going to see for the architecture, design architecture. The next stage of it is architecture. So we won't follow this. So we want. So in this stage we have several steps. So these are the main steps. So in each and every stage we have several other steps also. So as the same one, first after specification, the next one is architectural design. So architectural design made based on the specifications that you told by you. So what we are going to do is we are going to design the architecture. So how we are going to do this? So suppose this is my circuit, or this is my chip. So inside the chip, I have a processor, these kinds of processor. So I need an Intel processor. So I need a memory. So it need to be stored 512 KB memory. I need a RAM here. So I need a USB port. I need a HDMI cable. So all these, based upon all these things, we are going to design an architecture. Based on the specifications, we are going to design architecture. And later what we are going to do is we are going to design the code. So the code will be designed in form of RTL. So RTL is nothing but register transfer level. So what it is going to do? So it is going to explain about your design and how the data is flow in between a registers. So RTL is nothing but is an abstraction to design, to how to design your circuit and how the data is getting flowed inside a registers. So registers are comes under sequential circuits, right? So you can ask me here like, so don't we have any usage of combination circuits inside this chip? So we need combination circuits. So when we need this combination circuits, so to make delay in between registers or do some logical operation in between one input as a register, we are passing some input to your register, right? So when we need to pass our logic, or we need to pass some data with some delay. I want to pass data with some delay. So what I will do? So I'll add some gate here and add some delay gate, or I'm adding some buffer, or or I want to do, I want to collect some information from multiple blocks and I want to insert or I want to send it to a single block. So what I will do? So I'm going to use one adder or I want to go use some mux. So we have the usage of combination circuits and also we have the usage of sequential circuits. So sequential circuits are going to be stored inside the data. It is going to be stored data. We're coming to combination circuits, so it won't store any data. So whatever the data we are passing, it allows you to pass through it. That is the purpose of combination circuits inside your chip. Okay. So here that is mean by RTL. So this RTL code is written in HDL language, hardware description language. So what is this hardware description language? So how it is different from software languages? So hardware description language is of two types. So we can return our hardware or we can return our code. So in Verilog language, or we can return our design in system Verilog language, or we can return our design in VHD also, very high speed integrated circuits. So we can write any of these languages. We can write. So what this, how it is differs from the hardware, how software languages. What was the difference we have between hardware languages and software languages? So these hardware languages provide a flexibility to design the circuit by knowing the behavior. So by knowing the behavior, if you know the circuit behavior, so suppose I have a circuit, a RAM. So we know the RAM, right? So what was the purpose of RAM? To store the data and to get out the data. So to store the data for some amount of time. So that is the main purpose of RAM, right? So we know that behavior. That is the behavior of that, right? Can we design our circuit in software languages by knowing that behavior? We can't design. But this HDL language is providing that. So while describing our language or describing our circuit with a behavior, by knowing the behavior, what it is going to do is it is directly converts our design into gates. So usually when we need to design our circuit, when we are designing our circuit, so usually we are going to design with gates. So if you want to design your gate by knowing the structure diagram, so we are going to design. So when we don't know the circuit diagram, so we know the behavior of it. Can we design that? Can we design using software languages? We can't able to do. But these HDL languages is providing that. So that the way of writing we are calling as a behavior modeling. So we have different styles of writing our code in HDL. So we can write our, so that means it is providing that many flexibilities. So what are the different ways we can write our design? So if you see HDL languages, so there are different ways we can write it. There are different ways to write a code. So one is with behavioral modeling. One is with behavioral modeling. One is with the data flow modeling. One is with gate level modeling. And is with switch level. So these are the four types what we have. So HDL will accept this four behavioral modeling styles, and VHDL is accepting that. Sorry, Verilog will accept these four types of modeling styles. So VHDL will accept that, and the system Verilog also accept these four types of writing of your code. So what is this behavioral level modeling? So it is these language or these modeling style is used. So these are the different ways of writing your code. So in HDL language, so there are different ways to write your code. So these are the four types to write. So when we use this HDL behavioral model, so when you know the circuit behavior, we can use this behavioral modeling to describe that. So when you know the equation, so if we see our circuits, we'll have an equations, right? So if you see for full adder, what was the equation for sum and what was the equation for carry? So if you see for the full adder, we'll have, so if this is your full adder, ABC as your inputs and sum and carry. So it will have three inputs and four outputs, right? So what was the equation for sum? It is A XOR B XOR C. And what is for carry? A and B plus B and C plus C and A. So this is the equations. When you know the equations, you are going to follow data flow modeling. You are going to data flow modeling. And when you know the gate level circuit, so this is normal circuit. This is just what we know. This is the way to, this is the full adder, three equations. When you know the gate level circuit, how will be the gate level circuit of full adder? So we have an XOR gate for A and B with AB. So, so this is for C. So A XOR B, and this is given as an input to another gate. So this is C, and here we'll get A XOR B XOR C. And for carry it is AB and BC with AND gate and CA. C and this is A. AND gate, and all these three are connected to OR gate. So AB plus BC plus CA. So this is a gate level circuit, right? So when you know the circuit, you can use this gate level modeling. So we can design our circuits using gate level modeling. So when you know the transistors level, that means in form of transistors, PMOS transistors, and when you know the design with PMOS transistors and NMOS transistors, you're going to use this switch level modeling. Okay. So this flexibility is providing by HDL language. Only HDL languages is providing this flexibility. So that's why we are going to use HDL languages to design this. And moreover, why we need to write only in Verilog? Why can't we? So mostly we prefer to write our designs using HDL, or using Verilog language. Why we are not doing with VHDL, or why we not do with system Verilog? So that for that also we have it. So most of the tools after designing of your code, what was the next thing to be happen is, so the designed code need to be converted into gate level netlist. You are writing your code in form of textual language. This is a textual format. So we are going to write our design using textual format. So this textual format need to be converted into gate level netlist, right? So when you know the circuit, you will insert that circuit inside a layout. So that is what you are doing here. So you want to do that. So you need to convert this language. You need to convert this textual code into in form of gate level netlist. So only that is the process of converting your Verilog code. That is the process of conversion of your HDL code into gate level netlist. We are calling as a synthesis. So to only most of the tools will accept this Verilog language to convert into gate level netlist. So most of the tools, some of the tools will accept VHDL, and few tools will accept system Verilog. So, but all tools will accept Verilog. That's why mostly we are going to prefer to write our design only in Verilog. So after that, what we are going to do is we are going to verify the design after RTL code. So after we have finished RTL. So after RTL code. So did I need to say how to write this? They need to say how to write a code with just a normal basic Verilog code. So we'll discuss that. So So how we are going to, so we will see for full adder, normal full adder. So how we are going to write a basic code for full adder, we'll see. So whenever we are writing a code in Verilog language, so we are going to start with module and end module. So we're going to end this with end module. So these are the basic building blocks to design any of the circuit. So when if you see for any circuit, any HDL language circuit, so we'll start with module and we need to end with end module. So these are the basic constructors. So for each and every module, we have a module name. So we have a lot of circuits here. When you see for a lot of circuits, so to make it differ, we need to give a name to the module. So here I'm designing for full adder. I can give any name. So I can give any name. Just I'm giving my name as full adder. And after that, I need to declare my ports. So ports are nothing but your inputs and outputs of the circuit. So what are the inputs we have here? A, B, C are the inputs of a full adder, and someone carry are the outputs of the full adder. Outputs of the full adder. So the next thing is what? After writing this, so we need to differ what are the input ports and what are the output ports of the circuit. So I declared all my inputs. I declared all my signals of my circuit. And after that, I need to declare what are the input ports and what are the output ports of my circuit. So I need to declare my input port with keyword input. So it refers input signals. So what are the input signals in these? A, B, C. And what was the output signals here? Sum and carry. So these are the output signals. So after this, what we need to do? So we have written module and module. So we have differed with module name, and we have make a difference with the difference of my input ports and output ports. So I need to write my logic here. So we have different types of modeling styles. So I can follow any of the modeling style to design our circuit. Let's think I will follow gate level, data flow modeling style. So data flow modeling style is done when you know the equation. So we are going to use a keyword called assign. That means we'll have a continuous assignment statement. So where it is going to drive the data only to a file. So here these any of the combination circuits won't store any data. Just whatever the input we are passing, it allows you to pass through that. That is the one, right? So I'm going to write, or I'm going to, these are the wires here. So what I mentioned here, these are the wires here. So what I'm going to do is I'm going to assign my data to my wires. Sum equals to A XOR B XOR C. And I need to write for carry, right? So carry equals to A and B plus B and C plus C and A. This is the representation of RA and this is the representation of ND gauge. Okay, so like this we are going to design the code. So this is a small net to write a code. As the same way we are going to write the other codes also. So when you know the behavior or when you know the equation, so based upon the thing what you know, so the based upon the things what you know, if you know the equations, you can follow this. If you know the gate level circuit, you can follow that. So when you know the behavior, you can follow this. Your circuits can be designed with 10 years. Hello? Okay. So based upon the thing what you know, you need to follow that modeling style. Okay. So this is how your Verilog codes are getting designed. So the next thing is what? Functional verification. So the design thing will have a bugs, right? So the thing what you have designed is correct or not, you need to know. So for this, what we will do? So we are going to verify that. So that verification done is using system Verilog. So by using system Verilog, we are going to verify the design. So while coming to Verilog, we will verify our design in Verilog. So, but later on, why we go for system Verilog for verification? Because so as going on increasing, so the circuit complexity is getting increased as the days are going on. So complexity of the circuits is getting increased, right? So for that to increase, so to if the circuit complexities are getting increased, what we need to know? So the verification process is getting more complex. To make it easier, what we are going to do is we are going for system Verilog and we are going to change our test bench also. So while coming to Verilog test bench is nothing but a stimulus generator. So what it will do? So stimulus generator is nothing but your input generator. So when you want to when you want to check your design, what you will do? So suppose you have the same full ladder, you want to check it. So if you want to check that whether the design what you have done is correct or not, what you will do here? You will pass some inputs to your design. That's the same thing in the Verilog also we are going to pass some inputs. So how we are going to pass is we are going to randomize some data of my input values and I will pass that data from test bench to design. So what will happen? It is going to give some output and we'll check that output whether it is correct or not. This is how a normal test bench is getting checked. But later it is going on. So the test bench or the circuit complexity is getting increased. So what we are going to, so we need advanced concepts or advanced things to check your design. So for that purpose, we went for system Verilog to verify your circuit. To verify your circuit. So there we have modified our whole test bench. Usually we have only small block for the test bench. While coming to system Verilog, so we have increased the blocks. We have increased number of blocks in our test bench. So here we have a separate block to generate our stimulus and we have a separate block to monitor the values. So we're coming to system Verilog, we have monitor, we are sending the data, we are generating the data or we are monitoring the data within a single block itself. Within a single module itself, we are going to do that. But coming to system Verilog, what we have done is, so we have maintained a separate block to generate the values and we have maintained a separate monitor block to monitor so that we are monitoring. So we have kept a separate block to monitor and we are kept a separate block to drive the data from test bench to DUT and we have maintained a self check. So every time I can't able to check each and every output, right? So for that what I'm going to do is, so I'm going to maintain separate block which is exactly replicate of your design So whatever the inputs we are passing for the design and whatever the inputs what I'm passing for the design what I had in the test bench, if the both the inputs are same, so it is going to generate, it is going to pass the test case. So we have developed that kind of test benches in system verilog. And later what happen is, so we have modified, we have inserted some layout to your system verilog and we have named it as a UVM, universal verification methodology. And after system verilog we came for UVM, system UVM, universal verification methodology. So it is not a language, it's a methodology. So language is different and methodology is different. So why I came for UVM? So every time so suppose we have a project and we are working on that project. So what happened is, so in mid of my project, so some of my teammate got issue with my office and he left off. Then who will do that work? So I have my own logic, I have my logic, and I will return. And I can understand that. And you have that logic and you will write your own logic. And only you can understand that. If I see your code, I can't able to understand, right? So what will happen here? So a lot of, so to make it understand, what will be taking a lot of time. So if I give, so the project, the deadline of the project is coming within 2 days, and I need to finish that project within 2 days. But it is not sufficient to for me if I follow in system verilog. So for that, what it is? So they had came out with system verilog UVM to they need to follow the same pattern to write a code. They everyone need to follow the same pattern to write a code. So that so the logic will be the logic will be the different, but the pattern will be same. So it won't take that much time to understand my circuit, to understand my code. So for that purpose, we came up with system verilog. So we came with UVM, and we are going for that. Okay. So the verification is done in now. Currently, the verification is doing in UVM. So they not only in UVM, we have other methodologies also. We have OVM, UVM. So open verification methodology, UVM, universal verification method. So everyone will follow the UVM. Only few of the companies will follow open verification methodology. Okay. So now the verification is going to be done in UVM. Okay. And also in verification, what we have done is they had inserted few constraints. So it is not possible every time to insert A as 0, B as 0, C as 0. So we need to have different combinations. So for if you see for full adder, we have 3 inputs. So we can, which is having 8 combinations. So we have, if we have 3 inputs, we have 8 combinations. We can directly insert the value 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1. So as like that, I can insert. So because of small circuit. If it came from the large circuits, can I do it? I can't do. I can't do every time. I can't insert the value 0, 0, 1 as like that. Linearly, I can't do that. So for that is they had introduced for randomization concepts. So they had introduced few coverages. They had introduced some assertions in this function verification. So what these randomizations do? So it is going to randomize the data. So randomization, random keyword is used to randomize the data. So every time I can't be able to insert, right? So I'm going using the loops or by using some other concepts. We are going to randomize the data and we are going to pass that in. But when I'm randomizing the data, I don't have any control on it. So there is a chance of randomizing a single variable multiple times. So I want to cover 0 to 100 within 10 randomizations. So within 100 randomizations. So is it possible? No. So I don't know what are the values it is getting randomized. And there is a chance of repeating the values. So for that, what we are going to do is they're going to add few constants. So constraints are used to control your randomization. So how these controls? So in 1 to 100 randomizations. So if I had repeated my randomization 100 times, so let's think my 9 value is not randomized. So what I will do is I'll write a constraint to randomize that 9. So here I will check your 100 combinations. You will check my 99 combinations and it is working correctly. But I don't know this 9 randomization is not randomized and it is not working. If I increase the randomization count also, it is not getting. So for that, what I'll do is I'll write a constraint for that. Constraint is nothing but forcefully assigning a randomized variable what I want. So I need a 9 variable to be randomized. So I'm writing a constraint for that and it will be randomized the 9 and we will check that combination also. So what will happen here? Here all my combinations has been checked. So I need to, so is it possible like each and every combination is checked, each and every value that has been randomized is randomized or not. How we can know? So it is impossible, right? For that, what we are going to do is we are going to add some coverages. So these coverages will tell how much percentage the values has been randomized. So in between 1 to 100, how many, not how many values, how much of the randomized values has been covered. That means how 99% it is covered or 100% it is covered. When it will be 100%, when all the randomizations has been done. So at that time only it will be 100%. So here what we are going to do is we are going to add coverages to know how much of the randomization is getting success. So we are going to do that. And also we can do, or we can also add assertions. So what assertions do? It is when I run this code, when it is following the structure on it. So usually what we have after doing reset, so it should do the actual process. Suppose if we have a memory. So first of all, what we are going to do, if we have a RAM, what we are going to do? So usually the memory will be there in X. So RAM contains memory. Memory, it will by default, it is going to store X. We need to make from unknown to known state. That means we need to pull all my memory from XXX to 000 state. What we are going to do? We are going to do reset, and after the next cycle, I'm going to do my actual process. I want to write the data or I want to read the data. Next thing will be done when reset equals to 0. So this is how what I want to do. So what I'll do, so I want to check this condition. After one clock pulses, after reset is getting high, within the next clock pulse, my reset is getting 0, and at that time the data need to be stored inside a memory. So this is the one. This is a structure. This has to be done in an order only. So I'll write this assertion whether it is working or not. So it is running or not, or I'll write an exception for that. So if the randomized variables we can do, or we can check with coverages for these kinds of structure or these kinds of pattern, we can't able to do that. We can't able to observe these kind of pattern in coverages. So for that, we are going to write our assertions for that. So we are going to write the assertions, and we are going to check other or chip is getting, or the design what we have written is functioning or working well or not, we are working good or not, we are going to check with this functional coverage. So this is up to functional verification. And after that, what we are going to do is synthesis. So after that, what we are going to do is synthesis. Synthesis is nothing but the designed code. So verification, we won't do any verification. We won't touch any verification. After designing our RTL, we are going to do verification. If it's working fine, if it's working 100%, we are going to take the design and we are going to convert it into gate level netlist. And we are going to convert it into gate level netlist. So that means the designed code is converted into in form of gates. That is what synthesis means. And later, after finishing that, so we have another process. We'll say that. So after that, we have a DFT, design for testability. So what this DFT will do is it is going to improve the quality of your chip. So here what we are going to do is we are going to add some chains. So we have a few technologies or we have few methods. We are going to add that. So what it will do? So first thing what we are going to do is we are going to add some chains insertion. We are going to add some chains insertion. So what it is nothing but usually the gates are not made by us. So it is done by tool. So we are writing our code, and that code is getting converted into gate level netlist. So we are not, or we are any physically, we are making any transistors to arrange in that. So automatically it is done by tool. So it will be done in an order. So it is not done in an order. So it will do some randomly. So one of my register will be there in up, another register will be there in down, as there is a possibility for that. Another is an up, another is down. So we have a lot of space in between each registers. So by using that chain insertion, what we are going to do is we are going to arrange all our flip-flops in a serial order, in a sequential order. So what will happen further? Well, if we arrange, if we do this chain insertion, so what will happen? So the registers will be arranged in a sequence of order, and the space, we will get some space. So what will happen if we get the space? The size of the chip will be decreased. So this is the first method. What DFT engineer will do. This is one of the technology DFT engineer will do. And the next one is they are going to add some self-checking circuits inside the design. They are going to add some self-checking circuits. So what is this self-checking circuits? So when we are designing a circuit, so let's think there we got an error. So some of the block is getting an error. After designing that, so can we able to note down that? Can we able to notice that? We can't able to, after designing the chip, we can't able to notice it. So to make it noted, to automatically it is getting corrected. What we are going to do is we are going to add some self-checking test circuits inside our design. So this is the one. So another one is we are going to check the boundaries. So in boundaries, what we are going to, the connections are getting well or not. So whether the circuit is getting connected to VCC or ground correctly or not. We are going to output pins. We are going to check the output pins, input pins. Everything will be done in this DFT engineer. Everything will be done by the DFT engineer. So what will happen if we do this? So the quality of the chip will be increased, right? So the main one is to improve the performance of your chip and improve the quality run, right? So here by decreasing the size of the chip, the quality is getting increased. So this is done by the DFT engineer. So this is will be take care of the DFT engineer. So the next stage what we have is physical design. In physical design. So in physical design, what we are going to do is, so up to now we have written our code in form of textual format. So here in this physical design, they are going to arrange our circuit in a geometrical format. In a layout, they are going to arrange the circuits or the design. What we have done is they are going to arrange in a geometrical format, geometrical layout format. So in PD, we have different domains. So we have a floor plan. So we have a placement. Next one is CTC, and next one is uh, routing. So and physical verification, sign off, STS. So we have a lot of things in this physical design in this physical design. So first one comes under fabrication. So not fabrication, placements. Floor plan, not floor plan. First comes under floor plan. So what this floor plan will do? So they are going to add some memories inside your layout. They're going to add some memories, the macros that we are calling as a macros. They're going to add some macros inside the layout, and after that it will comes under placement. So in placement stage, what they are going to do is they're going to add some cells. Cells, simple the cells can be say as a gates. So the gates are going to be arranged in this layout, and that means the whole circuits will be arranged inside that layout. So after that, what will happen is CTC, clock tree synthesis. Clock tree synthesis will come. So in this clock tree synthesis, what they are going to do is they are going to apply the clock. They are going to give clock to each and every block. So suppose we have multiple ICs inside a chip, right? So we have a lot of ICs inside a chip, and each block will work on certain frequency. Each block will work on certain frequency. So one of my block is work at 100 megahertz. So another block we have work at 200 megahertz, and another block will work at 300. Or if you see for Ethernet, 156.25 megahertz. As like that, each and every block will work at certain frequency. Is it possible to give clock to each and every with from the outside? From the taking a pin from the outside, is it possible to give your clock to each and every circuit? Is it not possible, right? So the main aim is to decrease the size of the chip. So when we take this, when we take an external signal from the outside, and if we apply our clock to each and every block, so the size of the chip will be decreased. So it is not a good way to design a chip. So for that, what we are going to do is we are going to use a frequency divider concepts. So what is frequency divider concept will do? So wait a minute. So let's say this is my chip. So this is my block 1. This is my block 2. This is block 3. Block 4. Block 5. Block 6. These are my 6 blocks what I have inside a chip. So let's think this is working at 100 megahertz. So this is working at 50 megahertz. This is 156.25, and this is 200 megahertz, and this is 300 megahertz, and this is 400 megahertz. Let's see. So one or each and every block is working at different frequencies. So I can't give I can't generate 100 megahertz clock and I give to a single block, and 50 megahertz to another block, and 156 to another. So for each and every block, I can't generate each and every clock. For each and every block, I can't generate a clock. So for that, what we are going to do is we are going to use frequency divider concepts. That means what it will do is I'll generate a clock. I'll generate a single clock which is of highest frequency. So let's say this is the highest frequency, 400 megahertz. So I'll create a clock only for this. So and what I'll do is I'll divide this clock into the required frequencies what I want. So we have a frequency divider concept in our digital electronics. So we can divide frequency into multiple stages. So if I want to design, if I have a 400 megahertz frequency, let's say, if I have a 100 megahertz clock, so if I want 50 megahertz, I can make it into two. I can divide it into two. That is nothing but f by two circuits. So if I have 25% megahertz clock, I can make 100 by 4. I can divide these frequency, the topmost frequency what I have, so I can make it into 4, divide by 4. Then it will become 25 megahertz frequency. So we have a concept of frequency divider concept. We are by using that concept, we are going to divide our clock and we'll apply this to each and every block. Okay. So that is in CTC. So that is done in CTC. If they are going to generate or they are going to apply your clock to each and every block. Okay. The next will comes under routing. In routing, what they are going to do. So we have inserted lot of blocks, right? So we have inserted some macros and we have also inserted few cells in our layout. So did I connected this into any of my VCC or ground? To any of the power supply or no ground. So up to now I didn't do that. So I'm going to do that in routing. So that thing will be done in routing. So after that, what will happen is we are going for physical verification. So in physical verification, what we are going to do is, so we are going to check the timings or design rules or layout versus schematic. So these things we are going to design or we are going to check in. So when we design our RTL code, we have done our verification. So when we do the physical design, so that thing also we need to verify. So that thing we need to done in a physical verification, which is nothing but a sign of verification. So we are going to do timings. We are going to check the timings whether it is working correctly. So timings will be checked by CTC engineer. Sorry, it's not CTC, STA engineer. So STA engineer will do that, and we are going to check the design rules, and we are going to check the schematic versus layout verification. So everything will be done in layout verification. So after that, after finishing of everything, after verification of your design, physical design, what we are going to do is we are going to convert our physical design into GDS format, graphical design system. So we are going to convert that into GDS format and we are going to send, so that file, is a type of file. It is a type of binary file. So how your Verilog file system, Verilog files we have, right? As the same way, we have also a GDS file. So in this GDS file, what we are going to do is, we are going to send this layout in form of what we have in form of binary to a fabrication centers. So after that, fabrication centers what we'll do. So in form of under the guidance of, not under the guidance. So in under silicon wafer, they're going to develop a chip. So they're going to develop a chip. So after developing a chip, what we need to do? So they will pack it. So and they will pack it, and we are going to test that. We are going to test that whether the requirements what the client had given. So your specifications will be provided by the client only, right? So based upon the specifications provided by the client, so is it obeying all the things? Is it obeying the specifications what the client had given? So when it success all these things, we are going to hand over the chip to the customer. So client who are the project who had given to us, we are going to give that. So until that, we will take care of everything. Until that, we are going to take care of everything. So this was the VLSI design flow what we have. Okay. So what was the first thing? What was the first stage in VLSI design flow? Specifications. And after that, architectural design. And after that, RTL code, RTL design. And after that, RTL verification or functional verification. And after that, logical synthesis. We have synthesis. And after that, DFT. And after that, physical design. And physical design, we have several steps. One is floor plan, placement, CTC, clock tree synthesis, and routing. Next one is physical verification. So in physical verification, we have a lot of things. So sign off, STA, a lot of things will have. Next one is fabrication centers. So we are going to send. So after doing physical verification, we are going to make it into GDS file. So after taking the GDS file, we are going to send it to a fabrication centers. So well, coming to these fabrication centers, we have only 4 or 5 fabrication centers throughout the world. So up to now, India also don't have any fabrication center. Only recently with the $10 billion, Recently, they have started the fabrication center in Gujarat. So up to now, we don't have it. Within, if they developed or if they build that fabrication centers, within 2 to 3 years, so VLSI industry will be there in next level. If they done it within 2 to 3 days, so it will be there in another world. India will lead the semiconductor industry. Okay. So if you see that fabrication centers, so Taiwan have TSMC. TSMC have one fabrication center. So Intel have fabrication center, not in India. So it is in US. And Samsung have one fabrication center. And Global Foundries have one fabrication center. Only for and one more we have. So totally 5 fabrication centers we have in throughout the world. So and next one is after fabrications, what we are going to do? We are going to check it, packing and testing. So after testing that, we are going to hand over that. So this is the VLSI design flow what we have. We'll see. So this is what when you want to design a chip. So here we need to describe the specifications first. We're going to describe the specifications. The specifications should be as like, so what was the frequency, how will be the speed, and what was the functionality, size of the chip, and technology what you want, and type of chip. So you want your ASIC chip or FPA chip. So everything will be described here. And next one is RTL design and RTL verification after synthesis. Next one is physical verification, and next one is layout, analog layout design. So up to here, did we studied about analog engineers? So we have designed, we have seen our PD engineers or front end. So we'll discuss what is front end and what is back end. So we have designed RTL design and RTL verification, but we don't get any analog layout engineers. So where we get this analog layout engineers? So this will comes under physical design. So we want, sometimes when you are designing a chip, so we need a physical component to be kept inside a chip. So that will be made by this analog layout engineers. So we are going to this analog layout engineers going to develop the particular component or the particular block what they want. So they are going to develop that, they are going to test it, and they are going to hand over to these physical design engineers. And they are going to these physical engineers what they will do. So they will take that layout and they are going to insert inside that layout. So that is the purpose of analog layout engineers. And this is your transistor level circuit. And we're coming to physical layout. This will be like this. So it will be like this. So which you can't able to see. So lot of transistors are inbuilt inside that. So this is a physical layout. So inside the layout, they are going to integrate that. And coming to fabrication centers, fabrication is a process of creating integrated circuits on silicon wafer. So you're going to design your circuits under silicon wafer, and so in that fabrication centers, they are going to do etching, doping. There are several processes to that. So they will take care of that. They will take care of the design and packing and testing. And next, so in packing and testing, they are going to test it. And next one is, so to develop or to do everything inside this, so we are going to do with the tools only. So mainly we have 3 companies which provide tools. One is Synopsys, Cadence, and Siemens. So these are the 3 companies where they provide tools, EDA tools to us. So by using the tools, whether you're a front-end engineer or whether it is a design engineer or verification engineer or RTL design engineer or physical design engineer, so everyone will work on these tools only. So we don't have anything or so we'll have a software. So inside a software, we are going to work on it. Okay. So the next one is what is comes under front end, what is comes under back end. So every time, what are the different types of domains we have in VLSI, right? So we have a front end and we have a back end. So front end comes under RTL design, RTL verification. Front end comes under, and while coming to back end, we have physical design and physical verification. So these are the 2 things we have here in VLSI flow. So while coming to RTL design, so while coming to the front end, so front end comes under design of your specifications, architecture design, RTL code design, RTL verification. Up to there, it is comes under your front end. While coming to back end, it will goes for DFT, and next under physical design, physical verification. Up to sign off, it comes under physical verification. So physical verification or backend comes under PD and front end comes under RTL design and RTL verification. So what about this logical synthesis? So in mid of it, we have a logical synthesis, right? So both front end engineers and back end engineers both will take care of that. Just everything will be done on tool. Just whatever the code we have written. So whether front end engineer will take that or back end engineer will take that, and they are converted into gate level test. So everything just we need to insert that inside a tool. That's it. So it both logical synthesis comes under both front end and back end. Okay. So these are the different things what we have. So inside your PD, inside your physical design backend, we have an analog layout also. So analog layout also included in that. So if you are designing a code, we are calling as a RTL design engineer. If you are verification the code, so you are calling as a RTL verification engineer or design and verification engineer. And when you are so while coming to, so these are the two types we have in the front end, and while coming to the back end, we have PD engineers. In PD engineers, what we have? So we have an ST engineer, or we have a, so we have different, we have sign off engineers, so we have physical design engineers, physical verification engineers. We have a different domains in their backend also. So but whole over thing, the front end comes under RTL design and verification. Everything will be comes in a single term front end, and while coming to physical design and physical verification comes under back end. Okay. So the next one is VLSI design representations. So we are going to design our code, right? So when we are designing our code, usually our code, our circuits will be represented like this. So we are going to represent with some logics, right? With plus operator or AND gate operator. Usually when we are designing, it should be like this. So when we are converted into gate level netlist, so it will be converted in form of gates. So when actually what was the real circuit? The real circuit is in form of transistor level. So it will be like this. And when we are inserting that circuit inside a layout, so it will be represented like this. The fourth one. So this is how the circuits are getting represented. So this is the whole DLSI design flow. Okay. So we'll see why. So why these VLSI companies are paying a lot of salaries to these VLSI employees. So why? So I'll tell you a small example. So I have a project. And I go for I given to one company to design that. So the worth of this project is 500 crores. Let's think that is a mobile. So I had a given to design one chip. So which is for mobile to insert it in a mobile. So they had designed that project, and so I don't know. I didn't check it. I didn't check that. So in that chip we have a lot of bugs. So we have a lot of bugs. I didn't check it. So directly they had given me, and I given that into fabrication centers. So what will happen? They will made a chip, and so not they won't made single piece or two piece like that. So if they are making a chip, so they will make a chip in a big amount, bulk amount they are going to develop. So what happened? So they had given me 1,000 pieces, and the cost it has been taken to they had collected from me is like 50 crores. Okay, 500 plus 50. So it will take 550 crores to design the chip. So I had given to an external company to add some external devices, and let's say it will take another 50 crores, and I had given release to market, and I had released that chip to the market. So after releasing to that, so when I am using that, I don't find any errors. So after 1 month or 2 months, so they had found some issue. So I had found some issue in my chip. And what will happen? So I had released some sample 1,000 pieces. So when the stocks are going good, when the things are going good, so I'll release the remaining things also. So I had released only 1,000 pieces into the market. What will happen? They had within 1 month, so they had found some bug, and what they will do? So they will raise an issue. So can I change that issue? I can't change it, right? After fabricating a chip, we can't do any chip. So after fabricating a chip, so directly I can distribute to the market. So I can't do any modification. If I found any bug after manufacturing a chip, I can't do. So what will happen here? They will raise an issue, and no one will buy that. So I need to give the money since I had paid it, right? So I need to give the money to them. So what will happen here? So no one will buy these chips for me. So if I want to make a profit, I want to sell these chips. So no one will buy since had something founding some issue. So when we have an issue inside our chip, no one will buy that. So what will happen? So there will be a loss of thing. There will be a lot of loss to me, not to the company also. So I have already paid to the company. Company won't give me and the money to money back to me. So what I need to do here to make profits. I can't able to just I need to dump this whatever the chips what I made here. I need to dump in dump yards only. So I can't able to use it. So for that, what when why they are going to pay high amount of salaries is to find these bugs before getting designed, before getting fabricated. We need to make it. So this is a real time example what I had to. So recently we have seen OnePlus mobiles. So what happened recently? They had found one issue, right? So they had found an issue in display. So they're going some scratches or yes, we have got that. So why it happened? It is a bug. So which is not verified by the front end engineer or back end engineer. It is not fully verified. It is a bug. So what they had did to make it profit, what he had did. So just he replaced it. So he take that mobiles and he had given a new thing. So when you manufacture it, when you are going to manufacture a chip, so before manufacturing only you need to do everything. So after that you found if you found anything, so it will be a loss to you only, not to the company or not to the any other things. So that's why they are going to give their project to good companies which is having good knowledge people. Okay. So why they are going to pay high amount of salaries is this is the best example. To make it verified clearly, they are going to do that. And coming to the global semiconductor market, currently the VLSI market is or semiconductor market is about 600 billion crores, billions, so $1 billion. It is currently the market size of semiconductor is all about 600 billions, and in every year it is increasing 20 to 30% in every year. And the topmost companies what we have in this VLSI industry is Intel, TSMC, AMD, Nvidia, Qualcomm, and Samsung. These are the topmost companies what we have here. And India also launching a fabrication center in our Gujarat with $10 billion. So which is they are calling the programming name it as Semicon India. So they call name it as a Semicon India. So we the chip expert also is the part of that. So well, coming to here, so the way we are going to teach is we have an offline course and online course both in our chip expert. So we are going to teach online and all offline at a time, and daily we are going to take two classes. One is for morning and one is evening. Daily we are going to conduct two classes every day, and we are going to record the sections daily, and we are going to upload it in that e-learn portal, and you can access it daily, and it is a lifetime accessible. So you can watch the videos whenever you want. And we are going to have your tools. We are going to have all the tools. So we have a cadence tool, synopsis tool. So whatever the tools we want, we have it. So are the two licensed versions. And so we are going to take our meetings in June. So that two recorded sections. And we have a branch in Hyderabad too. We have a branch in Bangalore too. So and we have an experienced people to teach this VLS. Okay, so this is all about VLSI and VLSI design flow. So what are the things we have in VLSI? So how will be the VLSI design flow? What are the why we have VLSI engineers? So what was the purpose of VLSI engineers? So why VLSI engineers are paying a lot of salaries to their companies? So this is what. So if you have any doubts, you can ask me. So currently
So
it won't
hi,
be.
hello.
Yeah.
Yeah, so how much the duration of course? I mean,
So the courage duration of his course is around 6 months.
okay,
So in morning we are going to take one section and in afternoon we are going to take one section. So we are going to teach from basics. That means we are going to start our classes from transistors level to till end. So
okay,
transistors, digital electronics, everything we are going to take. We are going to tell you.
okay. But yesterday they told that only 3.5 months like that.
For what?
This analog layout only. 3.5 month. They told that 3.5 month only.
Who told you like that?
Yesterday I called to someone. I don't know that. I'm in Shark something someone.
I don't know. Once I'll discuss with them and I'll tell you.
Okay.
So usually we are giving 6 months of training to each and every domain.
Okay. Yeah. Okay. 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 Thank you.
Okay, then. So thanks for attending this section, guys. So goodbye, guys.
Yeah. Thank you.
Thank you.
Thank you.